In this video, we'll be discussing how to compare mean values between two different groups. Now, when we talk about a mean difference, we're talking about the average difference between two different groups, and this means that we're going to have continuous data. So this means either interval or ratio data, where the data is effectively infinite in terms of the numerical values that are possible for the endpoint that we're looking at. So an example of this could be heart rate. Now, obviously you can't have a negative value for heart rate, but it's continuous in the sense that you could have a heart rate of 48, 58, 68, 158. That would be a continuous data point. When we talk about mean differences, we would always use mean or average when we have parametric data, which means that it's normally distributed or bell-shaped or Gaussian distribution. If it's not, meaning that it's non-parametric, we would actually use medians instead of means, which is a separate set of statistical tests and in a separate video in this course. So for this video, we're talking about comparing means of two different groups where the numerical value that we're comparing is parametric or bell-shaped. So let's go through an example of an actual published article that compared means of two different groups. So this was published in 2022, and the title of the article was Filgrastim, Pharmacokinetics in Morbidly Obese versus Non-Obese Patients. And the objective of the article was to compare 15 obese patients versus 15 non-obese patients and look at the area under the curve, or the AUC, of this drug called filgrastim. And you can see here that they saw a numerical difference. It was 49.3 plus or minus a little bit versus 46.3 plus or minus a little bit, effectively a difference of 3. We use inferential statistics to decide whether that difference of 3 that we observe is due to chance alone. Is it different statistically than no difference, or a difference of 0? And we use a p-value, but we get that p-value using a statistical test. So if there was no true difference between obese and non-obese patients, we would have a numerical difference of 0. Assuming that there was no difference, our p-value would be very large and we would be right in the center of our bell curve. And what we would see is a large p-value indicating no statistically significant difference. But at the extremes here, when we observe some value that is really far left, meaning a negative value, meaning that the non-obese group had a larger mean, or some positive value where the AUC was much higher in the morbidly obese group compared to the non-obese group, at whatever those extremes would be, our p-value would be less than 0.05, and we would reject the null hypothesis, accept the alternative hypothesis, and we would conclude that there is a statistically significant difference between the two groups. So the way that we would actually test for that is called the independent sample t-test. Now there are some assumptions with all of our statistical tests, including the independent sample t-test, and we call these assumptions. They're basically things that have to be true in order to use that statistical test. So in this case, for independent sample t-test, we have to have a parallel design, meaning that we're comparing group A versus group B, and they never cross over, or there's not a pre-post study design. So in this case, you can see in the graphic here, we have morbidly obese patients, and they're completely separate in terms of how we treat them and how we assess them compared to non-obese patients. We also have to have exactly two groups. So we cannot use an independent sample t-test if we have more than two groups. So it has to be group A versus group B. We also, as we said earlier, the data that we're analyzing, so the AUC has to be normally distributed or parametric. And again, as the name suggests, this is an independent sample t-test. That means that our two groups have to be independent or unpaired from each other. So no comparing the same patient twice, no crossover. Now there are 3 synonyms for this test that we're talking about. In addition to an independent sample t-test, this test is also called a student's t-test, an unpaired t-test, or a two-sample t-test. Now where did these names come from? So a student t-test actually came from this gentleman on the slide, William Seeley Gossett. He worked at the Guinness beer factory, and he actually came up with this statistical test to analyze beer that was manufactured in the facility. And they used this statistical test for quality control, but the Guinness Beer Company did not want his name out there, so they just used a pseudonym of student. So it was published under the name of student as opposed to William Seeley Gossett. So that's where the name student t-test comes from. Unpaired t-test means that this is not a paired test. So paired testing is where we have a crossover or a pre-post design, and we're not doing that. This is independent. And then two-sample t-test is that we're literally sampling two different groups, and we get a different number between the two groups. There are things like a one sample t-test where you compare a sample versus a known average, which we won't talk about here, but all of these names refer to the same thing, which is an independent sample t-test. So going back to our example with filgrastim, we already said that there was a numerical difference that we observed of 3. And really what an independent sample t-test will tell us is whether that is a statistically significant finding or not. So in this case, the p-value was 0.6. So based on that p-value, we accept the null hypothesis that filgrastim's AUC is not different whether you're obese or non-obese. And because that p-value is greater than 0.05, we accept that, effectively saying that the difference is not statistically different from a 0. Or in other words, even though we observed a difference of 3, that 3 is due to chance alone, and it's as if there was no difference, which would be a difference of 0 in the study. Well, what about when we have a paired sample? We have a t-test just for that. So instead of an independent sample or an unpaired t-test, we also have a paired sample t-test. And this is used when we do have a crossover design or a pre-post design where we're studying the same group 2 different times. So as an example, imagine that we're comparing blood pressure and we give patients lisinopril for 6 months, measure their average blood pressure, and let's say that the first patient has an average blood pressure of 105, and then we give them an alternative antihypertensive like amlodipine, give them 6 months, and we see a blood pressure of 103. So the patient is serving as their own control arm, and we're really looking at the difference for that particular patient between treatment A and treatment B. That is a paired study design, and we'll use a paired sample t-test to analyze that. So again, in paired testing, the patient acts as their own control. That is a pivotal component of paired testing. So really, the null hypothesis is going to be that the mean difference is similar to 0. So between treatment A and treatment B, numerically, it's effectively 0. And we're going to statistically test whether the difference that we observe is close enough to 0 that we'll say there is no statistically significant difference. So just like independent sample t-test, a paired sample t-test has to only have 2 groups. So one assumption is that we still have group A and group B, but this is going to be treatment A and treatment B because we have the same group that we're studying 2 times. This also has to be parametric. So all of these t-tests are for parametric testing. And the groups are paired, as the name suggests. So this is either going to be a crossover or a pre-post design. So there was a study published in 2003 that compared albuterol versus the enantiomer levalbuterol in 10 patients, which is a really small study design, but it was a crossover. So patients got albuterol, and then later on they got levalbuterol. The study was looking at change in heart rate after getting albuterol versus levalbuterol in ICU patients. So the endpoint that they looked at was a continuous endpoint of the change in heart rate, and it was reported as a mean plus or minus standard deviation. So you can see here that we had albuterol versus levalbuterol, and what we saw was a difference of 0.8. So we're literally just subtracting 4.4 versus 3.6, and we're asking the question, is 0.8 different enough from 0 to be statistically significant? And we'd use a paired sample t-test to come up with the p-value, and in this case, the p-value was 0.03. So again, the null hypothesis was the difference between albuterol and levalbuterol is not different, or it's similar to 0. Because the p-value is small, we reject that, and we conclude there is a significant difference between albuterol and levalbuterol. That levalbuterol causes less of a heart rate increase compared to albuterol. But clinically, if you just think about it, even though we see a statistically significant difference, a difference in heart rate of 0.8 is clinically insignificant. So this is a great example of a statistically significant difference that is not clinically significant, because that small difference of 0.8 is not going to make a difference to a clinician or to a patient receiving albuterol or levalbuterol. So as a self-assessment, let's analyze whether we should use an independent or unpaired or a paired sample t-test for these study designs. So if we had a study comparing the mean time to sleep between patients randomized to either zolpidem or melatonin, which statistical test would be most appropriate, an independent or a paired sample t-test? So in this case, because we have two distinct separate groups, it's a parallel study design. So we would want to use an independent sample because there's no crossover. The patients are not serving as their own control. What if we looked at measuring cefepime half-life in patients, waiting 24 hours, then comparing the half-life with cefepime in addition to another drug called probenecid, which can impact the beta-lactam pharmacokinetics. So in this case, we have a pre-post design. Patients get cefepime, we measure something, then we wait, we give them cefepime again, but then we add an additional drug and then measure drug levels again. So this is a paired sample because the patient is serving as their own control. Then finally, compare average cost per patient before and after implementing a new pharmacy staffing model. So in this example, because each pharmacy is serving as their own control, this is going to be a paired sample again, because we're going to look at before and after. And when we see a before-after study design, that's almost always going to be a paired sample t-test. Thanks for watching. This video is actually one of 35 videos from ClinCalc Academy's Biostatistics RX online course. If you're interested in developing a rock-solid foundational understanding of biostatistics and medical literature evaluation, check out a link in the show notes, which includes access to the 35 videos, which is about 5 to 6 hours of content, more than 100 comprehensive quiz or exam questions, and even access to a free 10-question exam on biostatistics. Again, link is in the show notes, and thanks for watching.